All right, good morning, everyone. All right, so 8 o'clock, the official good morning. First thing, I just want to make sure that at least somebody has seen that the links to YouTube, or at least the first link to YouTube was posted in Canvas. If anyone in the chat just wants to acknowledge that, I'd appreciate it because I want to make sure everything is flowing correctly in Canvas. Besides that, I have a couple of details up on the screen for the moment regarding our next test and a few other details as well. So our second test is going to cover chapter 6, specifically the sections that we covered together through lecture and have homework assignments for, 6.1 through 6.3, and then 6.5. I'm going to be posting that test in my math lab on Monday. So I'm going to get that created over the weekend, and then I'll have it in place on Monday. I'm going to try and build the review before then. Hopefully I'll have the review up Friday, I want to say. And the review, I'm probably just going to make it an open My Math Lab assignment, like the homeworks, like the tests, instead of a printed out PDF. That way you can actually practice entering those answers into My Math Lab even more. So I'm going to post the test itself by Monday the 30th. What time? If I don't have it posted before our class, I will tell during the lecture what time it will be posted. And then I'm going to have it due Friday, and that'll be Friday by 11:59 p.m., just like we do with all the regular assignments. So I'm giving you a solid amount of time to work on this test. If this was going to be tested in class, because we'll be finishing 6.5 today, we would then have this test a week later. So I think this is pretty fair to go ahead and have it open and available. Now, the test has to be completed in one sitting. I want to add that. It's not like homework where you're going to be able to work on one problem and then take a break and work on another problem and take a break. I'm going to give you a 2-hour time limit, and I'm giving you 2 attempts. So also being very, very generous with this in case maybe you mistype something in my math lab. Maybe you're just not used to having to do a test inside of a computer program. I just want to give a little leniency with this crazy format that we're having to use now. I'm not really going to be giving partial credit because while I'm going to say this is a no calculator test and you have to use the provided formula sheet, I'm not going to be staring over your shoulders to ensure all this is going on. I'm not going to be able to check your work because I don't know if you've added something after the fact, after you've taken the test. Maybe you went back and looked at the answers and said, oh, well, my work says this. I just don't know. So I'm not really going to be able to give partial credit for the most part. Now, I didn't say I can't. I said it's going to be very, very, very rare. So maybe I can get you a couple points because you meant to type a plus or minus symbol and you wrote plus and then minus. For weird little things like that, if you bring them up to me, I can go and see if I can give you credit for that. But it's not really going to be partial credit for, oh, you had part of the answer right, but not the other part. So please do your best. Please practice this. Use everything to your advantage. I'm going to put the formula sheet in Canvas. I'm going to show you what that looks like here. And you're actually not going to see the bottom half of it. So maybe I won't let me move this. There we go. So this is, you're going to be your formula sheet right here. You're going to have your double angle formulas. Now I said I wouldn't give you the sine of 2 theta, just the cosine of 2 theta. Oh, actually, no, I said I was going to give you all of these. Wait, did I? It's been a while. There's a lot of craziness going on, so I'm questioning myself. No, I said I would give you the first one. So I'll give you cosine squared minus sine squared. I have the sine blipped out here, but I will change that. But I said I wouldn't give you the other 2 versions. I do remember that. I'm going to give you the tangent formula. I give you all the half angle formulas. And actually, I'm missing the other 2 that I said were better up here. So I have to edit this formula sheet clearly. But either way, you'll have an appropriate formula sheet. Chapter 6 homework is going to be due Thursday, April 2nd. So that is due one day before the exam. And the only reason I'm doing that is because technically the exam should be Wednesday. So a little leniency and same 11:59 p.m. Last thing, and I might not have to do this with y'all because I see 16 people in the room right now out of the, what we have, like 22 in the class maybe. So we've got really good participation for the live lectures. I'm not seeing that across the board. So what I'm doing to encourage my classes is I'm just throwing a random air quote quiz question into the lecture video, something super simple that, I mean, I'm basically going to say the answer to. And if I do one of those, I'd post it in Canvas and you have to answer it within 24 hours. Now, again, I don't know that I'm necessarily going to do that for us, but it would be completely random. I'm not going to tell you at the beginning of class there's a quiz. It's just maybe 45 minutes in, I'll say, oh, here we go. Here's a random quiz question. What is the color of the sky? Maybe something like that. Or what is the famous number from this movie or something? You know, just anything. It could be anything. It's not going to be a trigonometry question necessarily. And again, it would be simple if it was, and I'd probably just basically give you the answer. So again, that's to make sure that everyone's watching the lectures. And again, if you don't catch them live, you've got the YouTube links. Okay, so rant aside, let's get back on track. And we are in 6.5. We're continuing this. Let me move this first. There we go. 6.5 continued, and we're up to example 5. So we're going to solve this equation, and we're going to solve it on 0 to 2 pi. This is going to be 2 cosine squared of x plus cosine x minus 1 equals 0. All right, so we got 2 cosine squared of x plus cosine of x minus 1 equals 0. So if you missed last lecture, if you haven't seen that video yet, I gave a bunch of general strategies for solving these. And one of the first strategies was if that something is factorable, then factor it. Now, of course, with factoring, you want everything on one side, which I've already done that for you here. So we're going to try to factor this. And if you need to do a substitution, you can. You can say let u equal cosine of x. So then this is u squared here. This is a u, and the minus 1 is still there. Of course, the 2 is still in front. And then that might just make it a little easier to factor for you, pun unintended. But if you don't have to, then you don't have to. So let's do in red what some people might do. So you might, again, say let u, this is a pre-calc 1 technique, equal cosine of x, which makes u squared equal to cosine squared of x. So then our equation becomes 2u squared plus u minus 1 equals 0, which again just might be a little easier for you to factor. Trial and error or AC method, since there is a leading coefficient of 2. There's not a lot of options here, so I go with trial and error personally. If you want the AC method, that's fine. Literally the only option for the first term of each parentheses is a 2u and a u, because 2 times 1 is the only product that makes 2. The only options for the back is a 1 times 1, because 1 times 1 is 1. It's the only product that makes 1. But we've got to make sure that the difference comes out to a positive 1. Now the outer is going to be a 2, the inner is going to be a 1, so we need the larger number to be positive, so the product that makes the 2 needs to be positive. So that's going to be u plus 1 and 2u minus 1. Now let's go back to cosine, which would be parentheses 2 cosine of x minus 1 times cosine of x plus 1 equals 0. Now, all the stuff in red, again, some of you might not have to do. I don't care if you have to do it or if you don't do it. I just care that you can get to this point and that you factored correctly. Because if you factor in correctly, drastic things, I just lost my train of thought because of that. Bad things are going to happen. If this isn't factored correctly, obviously the rest of your solutions are going to be wrong, and it can make things generally a lot weirder. You should only be seeing quadrantals and things referencing the 30, 60, 90 or the 45, 45, 90. But if you factor in correctly, you put like a 5 here or a 7 somewhere, those values we're used to seeing are going to pop up. All right, so this is factored and set equal to 0. So we need to split this up as 2 cosine of x minus 1 equal to 0, or cosine of x plus 1 equals 0. Those are two unique equations that we're going to solve independently. For the 2 cosine of x minus 1, we're going to add 1 to both sides, which will give us 2 cosine of x equals 1. We're then going to divide both sides by 2, which will give us cosine of x is equal to a half. Let's work on the other one. If we subtract 1 on both sides, we get cosine of x equals negative 1. Oops, that button always gets me. Cosine of x equals negative 1. So these are the two equations we're trying to solve. Cosine of x equals a half, and cosine of x equals negative 1. Now this is a positive half, and cosine is positive in quadrants 1 and 2. I said that incorrectly. Cosine is positive in quadrants 1 and 4. I had sine on the brain, excuse me. Cosine is positive in quadrant 1 and 4 because cosine goes like x, and that's based on a smart trig class. So quadrant 1, that means that the reference angle will be an answer. And then to put something in quadrant 4, we'll have to do the 2 pi minus the reference angle. Cosine is a half, so let's just put that triangle up here. So x prime, that's our reference angle. Cosine is SOHCAHTOA, adjacent over hypotenuse. So this has to be the 1, this has to be the 2, making the opposite square root of 3, because that's the 1, 2 square root of 3 triangle. And therefore x prime, the reference angle, that's opposite the square root of 3, so that's pi over 3, aka 60 degrees. So 60 degrees is our answer, pi over 3 is our answer for the reference angle. That's also angle 1. So x1 is going to be pi over 3. The second solution needs to be in quadrant 4, so we do 2 pi minus pi over 3. That's 360 minus the reference angle. Remember, if you don't like dealing with radians, convert everything to degrees, and that's fine. We've only had a couple times where we absolutely had to have answers in degrees, but radians become much more normalized, so you're going to see me using these a lot more. 2 pi minus pi over 3, LCD there is 3, so that's going to become 6 pi over 3 minus pi over 3. So our second solution is 5 pi over 3. So we got our first solution, we got our second solution. Now these are the only two solutions from that first bit, because we're supposed to solve this on 0 to 2 pi. There was no number in front of the x inside, so we don't have to go through the n equals 0, n equals 1, equals 2 cases. Again, we only have to do that on a restricted domain if there is a multiplier inside, because that's what makes our waves go faster, as we related to last class. For the second equation, for the cosine of x equals negative 1, this only happens on a quadrantal angle. So this is either 0 or 90 or 180 or 270 or 360. Just really quickly, if we draw up our unit circle, please pardon that terrible looking circle. Remember our points, that's going to be 1, 0, that's 0, 1. We got our negative 1, 0, and there's 0, negative 1, which from the right point, that's 0 degrees, pi over 2, pi, 3 pi over 2, and 2 pi, and then you can just keep going around. Now cosine goes like the x. So cosine is like the x coordinate. I should really use a theta here. Sine is the y coordinate. Tangent, of course, is the ratio of the two. So we're looking for x coordinates that are -1. Well, the only x coordinate that's a -1 is right here, and that's at 180 degrees, which is pi. So our x is equal to pi. Now, there's only one solution to this, and I've mentioned this in class that sometimes with these you get 2, sometimes you get 1. If this had been a 0, there are 2 different points that have a 0 coordinate. It's the pi over 2 and the 3 pi over 2. We're looking for a -1. This over here is a +1, and that's why there's only a single answer for this. So that is our third solution. And if you wanted to have these all together instead of labeled individually, you can say x is equal to pi over 3. If you want to have them in order, the next one would be pi, and then 5 pi over 3. I do not believe the order should matter in my math lab. If it does, someone please email me and let me know. I especially don't want to have that be an issue on a test. That is something I would definitely give you credit for if it took points off for you not ordering the solutions by magnitude, by size. All right, so this is a pretty good problem. It's got your restrictions. So we didn't have to add the +2 in pi. It did not have any numbers in front of the variables, so we didn't have to, the same thing, we didn't have to add a 2 in pi and go through values of n equals 0, 1, or 2. And if you did try to do that, if you did add a 2 in pi to these solutions, because they're cosines, if you try n equals 0, you will get the 3 solutions found. If you try n equals 1, all of them would be too large. And that is a guarantee, because you'd be adding 2 pi to all 3 of the solutions. Now, if I had not said to solve on 0 to 2 pi, then you would have added the 2 in pi to the end of these solutions. That's the key difference, and that's something that people mess up a lot on with tests and homework problems as well, I suppose. Okay, let's try another. And let's change things up a little bit. We've been dealing with sines and cosines mainly. Tangent of x, parentheses, cotangent of x plus 1, close, equals 0. And I forgot to write, we're going to solve this on, I'll write it. Yeah, I'll write it here. Solve on 0 to 2 pi. Oops. Try to write this a little too high. There we go. Just trying to move my whiteboard. So we're going to solve this on 0 to 2 pi, just like the last one. And I've gone ahead and put this in a factored form. It could have been tangent times cotangent plus tangent, and then you take a GCF of tangent out. You could see that. Well, since it's factored and the other side's 0, we can go ahead and use our 0 product rule and set the tangent of x equal to 0. Or we can set the cotangent of x plus 1 equal to 0. So that's going to give us our 2 equations. The first one, tangent of x equals 0, is already solved. Well, I mean, it's already isolated. Tangent's already isolated, that is to say. So we just got to figure out what angles make the tangent 0. So going back to that unit circle, let's put that up here. With our points of 1, 0, 0, 1, -1, 0, same as before, and then 0, -1. I mentioned that sine is the y, cosine is the x. I mentioned this one but didn't write it. Tangent is the ratio of y over x. So tangent is the ratio of y over x. So we're looking for wherever the ratio of y to x is 0. The only way this ratio can be 0 is if the top is 0. So the top of this must be 0. The top is the y. So that means we're looking for y coordinates that are 0. Well, y coordinates that are 0 are right here and right here. Again, I'm gonna write that down just to make sure everybody gets that. We're looking for y. Oops, that silly button on the pen. Coordinate of 0. If this is set undefined, that means we'd want the bottom to be 0 and we'd want the x value to be 0 instead. So where are the y coordinates 0? Well, that happens at this point on the right, which is 0 radians, and this point on the left, which would be pi radians, also known as 0 and 180 degrees. So our x is, our solutions are 0 and pi. We don't need a reference triangle for that one. It had to be quadrantal. There's no way you could have an opposite over adjacent turn out to be 0 under a right triangle. That's saying that the opposite is 0. You can't make a right triangle with a side of 0. That's why we have to relate it to the unit circle. Okay, for the second equation, cotangent x plus 1 equals 0. We're going to subtract 1 on both sides. Got a little wild with that minus. And it's going to give us cotangent of x is equal to negative 1. Cotangent of x is equal to negative 1. Now you might think that this is going to be a quadrantal because, oh, well, there's negative 1 coordinates here and here. Remember, cotangent's going to be the x over the y. If tangent's y over x, that means that cotangent would go like the x over the y. But all of these ratios are either 0 or undefined, so it can't be any of those. So instead, we have to figure out which of the triangles it would be. So out of those two special triangles, again, we have our 1, 2, square root of 3, which is 30 degrees or pi over 6, and then pi over 3 here. And then we have our 45, 45, 90, which is 1, 1 square root of 2. 45, also known as pi over 4. So those are the two triangles, and we want the cotangent to be negative 1. Well, this negative is just going to tell us what quadrants we're going to end up being in, and cotangent is negative in quadrants 2 and in quadrants 4. So we're just trying to find a reference angle where this turns out to be 1. In other words, here's our reference angle. And we want the adjacent over the opposite to be 1, which is 1 over 1. That says this has to be a 1, this has to be a 1, and that's our famous 1, 1 square root of 2 triangle. So that says the x prime has to be pi over 4. Oops. Yep, that's right, x prime. Pi over 4. So that's our reference angle. But we said this has to be in quadrants 2 and 4, so we need to put pi over 4, that reference angle, in those quadrants. To put it in quadrant 2, we're going to do pi minus pi over 4. Which is 4 pi over 4 minus pi over 4. And that's 3 pi over 4. So that's our third solution. For our quadrant 4 answer, our fourth solution would be 2 pi minus pi over 4, which is, I gotta move my little bar. y'all probably can't even see. So LCD of 4, that makes this an 8 pi over 4 minus pi over 4, which gives us 7 pi over 4. So if you want to have all these solutions together in one statement, your x is 0, 3 pi over 4, pi, and 7 pi over 4. And again, I don't care if the answers were not in ascending order. I don't have to add 2n pi to any of these because this was a bounded solution set. The domain was bounded, and there were no extra numbers in front of the variables, so we have no reason to go through the n equals 0, n equals 1 equals 2 cases for that. Again, that generally only happens when you're doing a substitution on the inside, like with example, God, I'm looking back at my notes. Example 3a and b. Yes, example 3a and b. Okay. So again, I didn't have to give you this problem factored. You just need to know to move everything to one side and try and factor it if you see common factors anywhere. You have to watch out for your quadrantals. You have to watch out for your reference triangles. Or you can just have your unit circle absolutely memorized, which is going to be interesting as you move forward in math classes and have to memorize even more. Again, I know I've said this 1,000 times, but it's just an opinion. I think that having the unit circle and these two triangles is a lot easier than just blanket memorization of a whole lot of numbers. But you do what you need to do. What did I want to say? Oh, yes, now I remember. Please note with that previous example, do I have space to write it over here? Not really. I just wanted to point out that if this was an unbound problem, in other words, if I had not said to solve on 0 to 2 pi, if I had just said solve, if all I said was solve, the solutions would have been x equals n pi and 3 pi over 4 plus n pi. Now, how did I come up with this? Well, remember that tangent has a period of pi, not 2 pi. So if this was an unbounded problem, you would have only had to have found the solutions in quadrants 1 and 2, and then just add n pi to each of them. Going back to last lecture, we reminded you that the period of tangent was pi, whereas sine and cosine were 2 pi. So instead of adding 2 n pi to these solutions, you would add n pi because they're tangents and cotangents. Well, 0 and pi, these two solutions are picked up by this n pi. If you let n be 0, 0 times pi is 0. If you let n be 1, 1 times pi is pi. And then if you let n be 2, you'd get 2 pi, then 3 pi, then 4 pi, then 5 pi, et cetera, et cetera. So that would make sure you get all of them. You wouldn't have to say 0 plus n pi, comma, pi plus n pi, because that second thing is the same as the first one, just with slightly different values of n. The part of the solutions that were the 3 pi over 4 and the 7 pi over 4, if you add pi to 3 pi over 4, you get 7 pi over 4. So this second solution is picked up from the first one by adding an n pi. So this is just a way of compressing those solutions into 2 bits instead of 4. But again, you'd only want to do this for unbounded. For a bounded problem, you need to have the exact numbers. You don't want to see n's anywhere. Okay. Now we'll do example 7. and we're going to just solve. I'm not saying there's boundaries this time, and we're going to do sine of x minus 2 sine of x times cosine of x equals 0. Okay. Everything's on one side, and there is a common factor, so we should definitely factor this. There's a GCF of sine of x. It's in both those terms, so we'll take the sine of x out. When we divide sine of x by sine of x, you'll be left with 1, then a minus. When you take the sine of x away from this term by division, the sine's gone, and you're left with the 2 in the cosine. Equal to 0. Well, this is factored. There's no quadratic terms or anything like that, so this is as much as we need to factor it. We can use our zero product rule, ZPR, zero product rule. That's where we say the sine of x is equal to 0, or 1 minus 2 cosine of x is equal to 0. It looks like a 2. Let me rewrite that. I feel like I'm getting a little better with this, but I'm still working on it. Sine of x equals 0. I'm not going to redraw those unit circles again. Let's just go back to where we drew it last. Sine of x equals 0. That means we're looking for a y coordinate that's 0. So out of these points where there are y coordinates of 0, well, that would be at 0 and pi. Huh, that's kind of interesting that I gave you the same two solutions as the last problem. It was a coincidence. It doesn't mean anything. But again, here's a y coordinate of 0. Here's a y coordinate of 0. That's 0 and 180 degrees, or 0 and pi radians. So there we go. X is equal to 0 and pi. Now that's just inside of the 360 degree range. We will be adding 2 and pi to those. Okay, the 1 minus 2 cosine of x equals 0. If you want to subtract 1 on both sides and then divide by the negative 2. If you prefer, you can add 2 cosine of x to both sides and then divide by positive 2. Either way, you'll get the same equation in the end. It's just linear algebra that we should all be experts on by now. Divide by negative 2. And that gives us cosine of x is equal to a half. Well, that's definitely going to be one of the two reference triangles, and this is positive. Cosine's positive in quadrants 1 and 4. In fact, I believe we solved this earlier. Yep. Cosine of x equals a half. Cosine's positive in quadrants 1 and 4. We rationalized why the solutions were pi over 3 and 5 pi over 3. This is exactly the same as part of example 5. So instead of having to rewrite all of that, I mentioned last class, if you ever see the same equation twice in one sitting, you can just write down by example or by problem number, this is the solution. So let's do that. So by example 5, the x is pi over 3 and 5 pi over 3. So these are our 4 solutions inside of 0 to 2 pi. But there were no restrictions. This did not say to just solve from 0 to 2 pi. This said solve, which means we have to find every single possible solution in the world, and trigonometric functions are periodic. There's infinitely many solutions. So we have to add our 2 in pi to these solutions because of the unboundedness. Now, this first solution, 0 plus 2 in pi, 0 plus anything is the anything, so that's just 2 in pi. So the first solution, you're not going to even see the 0 in there, just like in that asterisk memo note I made from example 6 if it was not restricted. The 0 you didn't see, you just saw it as an in pi. Because if you let n be 0, all this jazz goes away. The rest of them, you have to literally add the plus 2 in pi, plus 2 in pi, plus 2 in pi. So x is equal to 2n pi, comma. The next solution in magnitude would be the pi over 3 plus 2n pi. Sorry, I heard a weird noise. I don't know what that was. I think it was someone leaving. Then the next solution in magnitude would be the pi. So we go pi plus 2n pi. And then the final largest solution is 5 pi over 3 plus 2n pi. Those are our 4 solution sets. Someone just asked, shouldn't 2n pi just be n pi? If these were tangents or cotangents, that would be correct. But sines, cosines, secants, and cosecants have a period of 2 pi, which is why we have to add 2n pi. Now, what you might say, and I was getting to that point. Now, what you might say is that, well, 0 and pi, and the next one would be 2 pi and 3 pi. So yes, you could actually take the first and third bit and compress them into one solution. So that is, I'm holding my pen upside down now. So you can write this in a slightly simplified form as n pi, comma, pi over 3 plus 2n pi, to n pi, comma, 5 pi over 3 plus 2n pi. That is just a more condensed version. It makes us have what looks like 3 different bits instead of 4, but both of these are acceptable. If this had been a tangent or a cotangent, we mandate that you have to use n pi wherever necessary. So that first one and third one have to be condensed, but this is acceptable because it's sines and cosines. So thank you for bringing that up. All right, so once again, we had to solve this. It was unbounded, so we knew that we needed some n pi's or 2n pi's in the answer. We saw the common factor of sine x, so we factored it out. We set each factor equal to 0. We needed to use quadrantals for the first one. We had to use a reference triangle for the second one. In fact, we were able to shortcut that just by referencing a previous example. But if you showed the work again, if you didn't recognize that that happened, the work should have looked identical back to example 5, which this was our reference triangle, which gave us our reference angle, which is the first angle because it's positive in quadrant 1 for cosine. Then it's also positive in quadrant 4, so we put the reference angle in quadrant 4. Okay. Moving on. Example 8. And we are going to solve. So this is unbounded. And we got sine squared of x minus 4 cosine of x plus 4 equals 0. This is the most interesting problem we have seen thus far, at least in my opinion. And of course, interesting usually means there's a quirk to it, there's a challenge to it. And that is that it's not factorable right now. We have a squared term and a linear term, pardon my yawn, but they're not the same trigonometric function. We can only factor something if it's the same trigonometric function, like back in example 5. Those are both cosines, cosine squared and a cosine. This one's got a sine squared and a cosine. So this isn't what we want to see here. Well, if you look back at your instructions on on just strategies, we mentioned that Pythagorean identities might be helpful, double angles as well, or any just other formula. Half angle formulas can be useful. I generally don't throw those at you, but they could be useful. All right, so let's use one of the Pythagorean identities. And obviously we don't need one with tangent squared or secant squared or cotangent or cosecant squared. This is a sine squared, this is a cosine. We're trying to make them both the same type of trig term. So let's use the fact that sine squared of x plus cosine squared of x is equal to 1. And if we solve that thing for sine squared, we subtract cosine squared on both sides. And that says that sine squared of x is equal to 1 minus cosine squared of x. The reason I solve this for sine squared is because I have a sine squared up here. This is a regular old cosine. I don't want to solve for cosine squared because this is a cosine. Now, I'm sorry, I don't want to solve for cosine squared because this is a cosine. I did say that correctly. If this was cosine squared, then maybe we'd want to do that instead. All right, so wherever I see a sine squared, I'm going to replace it with 1 minus cosine squared. So this becomes, and I'll use a different color just to show the substitution, 1 minus cosine squared of x, then minus 4 cosine of x plus 4 is equal to 0. There are like terms, the 1 and the 4 make a 5, but that's it. So this is going to be negative cosine squared of x minus 4 cosine of x, and then plus 5 equals 0. Now we only have cosine squared terms, so now we can factor this. But I don't like something about this. I don't like the fact that the leading term is negative. I have never liked factoring leading terms with negatives. Most students have a hard time factoring with negatives. So you can either move everything to the other side by adding cosine squared, adding 4 cosine x, and subtracting 5 on both sides. Or you can take a shorter approach and just multiply both sides by negative 1. So we'll take negative 1 times the entire left side, and negative 1 times the entire right side. Which will give us positive cosine squared plus 4 cosine of x minus 5 equals 0. Now, if you need to do that substitution again, you would say let u equal cosine of x, which would make u squared cosine squared, and then you'd end up with u squared plus 4u minus 5. I'm going to skip writing that this time. Again, if you need to do that, I've just verbally explained it. You'd say let u equal cosine of x, and that would make u squared cosine squared. And that would make it similar back to example 5. I'm going to skip showing the let work and just go straight to the factored form. And we're trying to find a factor pair that multiplies to negative 5, but subtracts the 4. Well, 1 and 5 would be the option. So we're going to go cosine of x in the first spots. Those would be the u's otherwise. And we know we need a 1 and a 5, so we'll go 1 and a 5. I don't need to do trial and error because there's no number in front of the cosine squared. I don't need to do AC method either. But we want to make sure that the 1 and the 5 subtract to a positive 4, so we need a positive 5 and a negative 1. So there's our factored form. Now we can use our zero product rule. Set each factor equal to 0. Okay, cosine of x minus 1 equals 0. We're going to add 1 to both sides. Which will give us cosine of x equals positive 1. That can only happen on quadrantals. That's when the x or the y coordinate is 1. Cosine goes like the x coordinate. So we're looking for x coordinates that are 1. And I'm just going to flip back to the last time we drew a unit circle with the quadrantals. So we're looking for x values of 1. x values of 1. Well, here's an x value of 1 right here, and that occurs at 0 radians. This is a -1, and that's not what we want, so there's only one of these. It's just 0 radians. So x equals 0. For the second one, for the second equation, we're going to subtract 5 on both sides. And this is where things get interesting, if they weren't already. Cosine of x is equal to -5. I would like for anyone to try and draw me a right triangle where its adjacent over its hypotenuse is equal to 5. Ignore the negative, just go with the reference triangle. It's impossible because cosine as well as sine, they are bounded between 1 and -1. And let me, instead of just saying is bounded, has a range of -1 to 1. We have never seen a cosine value be larger than 1 or smaller than -1. And that's because a hypotenuse is always, always, always going to be bigger than the adjacents and the opposites by the Pythagorean theorem. A squared plus b squared equals c squared. That says that the hypotenuse has to be the larger value. So how could we have a fraction of the adjacent over the hypotenuse be larger than 1? The bottom is always bigger than the top. So how could that ever be larger than 1? Let me say bigger than or equal. Bigger than or equal because they can match. And that's how we get the ratio of 1, like in the first solution we just saw. So this is impossible. And we also saw this in the graph of cosine. We saw the graph of cosine. It started at a height of 1. It went down to a height of -1 and then back up to a height of 1. Unless it had an amplitude factor in it, which there is no amplitude factor here. So what that means is we have something that can only take on values between -1 and +1 set equal to something that it can't be. This is an impossible equation. It's a trash equation. It means there's no solution to it. This can happen for sines. This can happen for cosines, but that's it. Cosine and sine have ranges of -1 to +1. The reciprocal functions secant and cosecant have ranges of everything bigger than 1 and everything smaller than -1, as well as those borders are included. So you can get no solutions to a cosecant or secant problem, but that's when they're between -1 and 1. It's quite the opposite of what's happening here. Tangents and cotangents can take on any value. Their graphs were unbounded vertically. Their ranges were -infinity to infinity. They kind of looked like little parabolas or little cubic functions, specifically the cubics. But it's not that this whole thing has no solution. We still found the 0. So there was one solution that we found from all this work. But you can't just stop here because we did not say to solve on a bounded solution set, on a bounded domain. We said to solve. So the 0, because it's a cosine, we have to add that 2 in pi. So x equals 0 plus 2 in pi, but 0 plus anything is the anything. So x is equal to 2 in pi. In other words, it's every multiple of 360 degrees. Again, it is my opinion that this is one of, if not the most interesting problem that we do together. You've got to use a Pythagorean identity so that you've got everything in one single trig term. Now you might say, well, we didn't have to do that previously. Where was it? Example 6. Example 6 had tangents and cotangents. Yeah, but it was already factored, or if it wasn't, it would have been easy to factor. You wouldn't have seen any tangent squares or cotangent squares. It's when you see those that you might have to do a Pythagorean. I say, oh, we'll go back to example 1 and do Pythagorean. No, these were already the same type of trig functions. If you were to turn this into 1 minus sine squared, now you have different trig functions, and you've made things worse for yourself. So you're only using these Pythagorean identities when you have two different types of trig terms, a sine squared and a cosine, or maybe a cosine squared and a sine. If you see sine squareds and cosine squareds, that would also be a reason to use the Pythagorean identity. All right, we got time for one more, it looks like, and this will be the last of the section. I'm doing a lot of these because I feel like we need to see a lot. There's a pretty good variety to them. So let's solve. And we're going to do 2 sine of x cosine of x is equal to 1. 2 sine of x times cosine of x equals 1. I did not give bounds, so we will have to add a 2n pi or an n pi or something to the solution set, ultimately. Well, this is annoying. The left side kind of looks factored, but the right side's a 1, which means it's not in an appropriate form. If you subtract 1 on both sides, it's not really going to be factored because you've got the sine and the cosine next to each other, then the minus 1. So this is a problem. We can't just go set 2 times sine of x equal to 1 and cosine equal to 1 either. We need this to be in just one type of trig term, just a sine or just a cosine or a tangent, cotangent, or whatever it might need to be. This left side looks really, really familiar. It kind of looks like, have we seen something? Let's go back. Not 2 first. Sine of 2x, sine of 2 theta, let's say 2 theta, equals 2 sine of theta cosine of theta. That was our double angle formula for sine. We had 3 of them for cosine. We had 1 of them for tangent as well, but that was the sine one, just a refresher. And if you look at that left side, the left side of our equation is the right side of the double angle formula. So that means that the left-hand side is going to become, I keep wanting to write the 2 first, please excuse me on that. It's because I'm looking at that 2. Sine of 2x equals 1. And that's because the left-hand side is the double angle formula. And in the instructions I gave you at the very beginning of the section, one of the strategies was use a double angle formula if you can. And that was a double angle, so we need to do that because that will condense things to just one trig term. So now we can try and, wait a minute. That doesn't just say a sine of x, that says a sine of 2x. And if you go back to last class, we said that we need to do a substitution for this type of problem. So we have to say, and I'll use some color for this, let theta equal 2x. This is the same type of substitution that we did previously. We don't know how to set up reference triangles or quadrantals if the inside is not just the variable. So we have to do a substitution, which will make this the sine of theta equal to 1. So instead of 2x, I'm now writing a theta. Okay, sine of theta equals 1. Well, that's got to be a quadrantal. So we're going back to our unit circle and trying to look for y values of positive 1. Here's our unit circle with the quadrantals. We're looking for y values of positive 1, which is this point at the top, and that point represents 90 degrees, also known as pi over 2. So theta is equal to pi over 2. All right, But we don't want solutions in theta, we want solutions in x. I gave you a problem in the American dollar. We decided to convert it to pesos. So the pesos solution is pi over 2, but I want the answer back in the American dollar. So we got to go back to x. But before that, remember that the period being 2 pi is only true for the substitution because there was there was a period factor here. This makes the period change. This period is actually pi, spoilers. But when you write it this way, the period's 2 pi. So we have to add the 2 in pi before going back to x. I mentioned last class that this is one of the most common mistakes people make is they'll go ahead back to the x, then add the 2 in pi. But the period, when you have it as a 2x, is not 2 pi. So theta is really equal to pi over 2 plus 2 in pi. That's theta. Now we go back to x. We said theta is supposed to be 2x. So the left side, instead of writing theta, we are going to write 2x equals pi over 2 plus 2 in pi. That's a very sloppy pi. And to solve this for x, we're going to divide all terms by 2. So divide the x term by 2, the pi over 2 by 2, and the 2 in pi by 2, which will give us x equals. Now remember I said dividing a fraction by a fraction, dividing by 2 is the same thing as multiplying by a half. So pi over 2 times a half, you take the 2 times the 2, which is 4. So that becomes pi over 4. Please show that extended work if you have to, but we've done that dozens and dozens of times in class already. And then the 2's here are just going to cancel. So that's going to be a plus in pi. That is the unbounded solution. And look, the period addition ends up being in pi. That is ultimately because there was a 2 here. And if we did that graphing process, we would say that to take the period of 2 pi and divide it by the coefficient of 2. 2 pi divided by 2 is pi. But the issue is you can't just add this on to the pi over 2 and say you're done, because in the process of doing this division, it changed the pi over 2 to a pi over 4. Oops. So that's important. You've got to make sure that you are doing this process, I keep writing on accident, down to every last detail. So please, please, please make sure that you are taking care of every single little detail. Hold on for a second. I've got someone at my door. I will be back in 20 seconds. Yes, sir.
Hey, are you authorized by the provost to work in your office here? I'm just asking.
I don't know. I just saw that we were close to the public. I was assuming that faculty were still allowed to be in here. All right, I'm back. And where did we leave off? Okay. So we got all our examples done for these equations, and that will close out the chapter. So again, this test has a very, very small number of sections on it. It's only 4 sections, but that's not to say that it's going to be an easy test. It's not going to say it's going to be a short test. It'll still be, the hour and 15 minutes it should have been for class. I'm just going to give you a little more time for working on the test. Let's do this. So in case anyone came in a little bit late, I'm going to put this back on the screen for a minute. Just to remind you that test 2 covers those 4 sections of chapter 6, which we have now completed. I will be posting your review hopefully tomorrow. I was just informed of some complications. Apparently, I'm not even supposed to be in my office anymore. So I look out for an email from me. I'm not even sure if I'm going to be able to do Monday's lecture now. I've got to figure something out because my technology at home is a little more limited. So check your emails, make sure you hear from me. But anyways, review, I'm going to try and get that posted tomorrow, but it'll be up no later than Friday. The test will also be going up on Friday. You have almost a full week to work. I'm sorry, the test is going up on Monday. I was looking at this Friday. So the review will go up Thursday or Friday. I'll email you when I post the review. The test will go up on Monday. I'll email you when I post the test. And then the test has to be completed in one sitting. You'll get 2 attempts. Make sure to quadruple check your answers. I'm not necessarily giving full credit, partial credit or anything. Formula sheet is going to be in Canvas. I'll let you know when that's there. Chapter 6 homework is due on Thursday, and I might do the occasional random quiz question. Besides that, if you have any questions, please email me and let me know. Besides that, have a good day, have a good weekend, and I will see you in the digital world on Monday, one way or another. Take care.